Yeah, what I wanted to talk about today is some recent work in Gaussian process regression, and in particular applications in inverse problems and Markov chain Monte Carlo. So this is joint work with my colleague Kostas Sigalakis, who many of you might know. He's also here in Edinburgh, and our joint student Tianming. Right. So the outline of the talk is the following. So I'm going to start by just introducing Bayesian inverse problems, so just introducing the type of problems that we're interested in solving. I'm then going to explain how Gaussian process regression comes into the picture and how you can use Gaussian process approximation or Gaussian processes to get approximations of the posterior. So the posterior distribution, which is the solution to this Bayesian inverse problem, is something that's usually quite complicated to deal with in practice. And so you have to use approximations which are more easily computable in practice. And then in the end, I'll talk a little bit about how this works specifically for inverse problems in PDEs. So most of the stuff that I'm going to be talking about applies to completely general inverse problems, but there's a bit more that you can do, in particular if you know that your inverse problem is based on a PDE. Okay, but hopefully all of this will become clear by the end. Right. So as I said, we're interested in solving inverse problems. So what are inverse problems? They're really just problems that are concerned with determining causal factors from observed results. So putting it a bit more mathematically, you want to determine the values of inputs that were given to a system based on partial and noisy observations that you have of outputs of the system. Right? So these are typically in applications where you can measure the outputs. So you can get observations of the outputs. You can't really directly get observations of the inputs, but you do want to know what the inputs are. And so you're using the observations that you have on the outputs to determine the inputs. So mathematically, that will look something like this. So we assume that we have some unknown parameters u. This is what we want to determine. We can't measure u directly. What we can measure is g of u. So g is some observation operator here. And then we get our data y. And typically this is corrupted by some noise. So the eta here represents observational noise, which, for example, comes from measurement error. So the instruments that you're using to take your measurements are not calibrated exactly, or they only give you, say, 2 significant figures or something like that. And so there's usually some noise in your observations. So in general, this is what the inverse problem will look like. We want to determine u given the observed data y. And what exactly this observation operator g looks like then depends on the inverse problem that you're interested in, and it can look very different in different applications. Right? So these appear in very many application areas. Big one is computational imaging, which has a lot of applications in medicine and astronomy, and also a lot of geophysics and climate and weather-based applications also have these kinds of problems. Right? And what the G will look like will depend on the particular application. I'm particularly interested in problems that involve PDEs, so partial differential equations. So one example of an inverse problem is the following. So you have some measurements of the water pressure at some locations. So we're considering groundwater flow. So the water is flowing through the ground, for example, in some formation that looks like this. And what you want to know is the value of the hydraulic conductivity K at different points. And observations that you have are from the water pressure. Right? Mathematically, this example looks like this. So we have a PDE model that kind of governs the physics that's going on, so the flow of the water underground. P here is the water pressure. The K is the conductivity of the soil, and the G are source or sink terms. This just comes from physics, so it just comes from Darcy's law plus conservation of mass. And so the permeability K and the water pressure P are implicitly linked through this PDE. What we have in terms of observations is the PDE solution P at some points in the domain xi with some noise. And what we want to learn is the conductivity K. And in particular, we're then assuming a parametric expansion here. So we assume that K can be expressed in terms of these basis functions phi j, and then we just want to learn the coefficients uj in this basis expansion. Right. So in principle, the inverse problem that we have is that we have data which corresponds to the PDE solution P, and we want to use that to infer what the diffusion coefficient K is in this PDE. Right. But as I said, this is just one particular example. And so in general, the G can take many different forms. And in general, we would just have this inverse problem where we want to determine U from these observed data. So you can see where the name inverse problem comes from. You essentially want to invert this observation operator G. That's usually not possible. One, because you don't know the value of the noise, and two, the problem is typically ill-posed and or ill-conditioned. So ill-posed means that G inverse simply doesn't exist. Ill-conditioned means that G inverse does exist, but it's very ill-conditioned. And so if you want to use G inverse to compute things on the computer, that would be a very numerically unstable method, and you would get very large errors in the computed solution. So that's typically not an option. One way to circumvent these problems is to use a statistical approach, so particularly a Bayesian approach. You treat your unknown U that you want to find and the observed data Y and the noise eta in the data as random variables. And then you follow the standard kind of Bayesian prior to posterior update. So we choose a prior measure on our unknown parameters U. I'm going to denote that density by pi 0. The way you choose this, again, depends very much on the application. So for the PDE example, for example, we know that the diffusion coefficient K is always positive. And so that's something that would influence your choice on the parameters U. You then look at the likelihood of the data. So this is the probability density of observing the data Y given a particular value for your parameters U. The way that you get this is from your observation model. So we're assuming that Y comes from G of U plus eta. If you fix U, G of U is just a constant. And so assuming that the observational noise is Gaussian with mean 0 and some covariance matrix gamma, the Y of U is just the same Gaussian, just with G of U added onto the mean. And so we get this form for the likelihood here, where I've hidden the constant because it's not that important to us. Then you can do the standard update using Bayes' theorem. So we get the posterior on U given Y as the product of the prior times the likelihood multiplied by a normalization constant, 1 over Z here, to make sure that everything is a posterior or everything is a probability distribution. So you have to make sure that this PDF pi y u integrates to 1, which is why you have this normalization constant there. So that's in the Bayesian framework, kind of the solution to the inverse problem, right? So remember, the inverse problem was to find U given the observed data Y. And so this distribution of U given Y is kind of what we're after in this context. So in applications, you then are usually interested in one of these two things. So you might want to produce samples from this posterior measure, for example, using Markov chain Monte Carlo methods. You can use that to compute expected values or probabilities or quantiles or whatever you want. And so whatever you're interested in about this posterior, or you might want to compute a point estimate for the unknown parameters U, so something like the map estimate, where you're just looking at the most likely point under the posterior. Yeah. Both of these things become computationally very expensive for modern applications. So if you, for example, think of sampling with Markov chain Monte Carlo, what you have to do is you have to repeatedly evaluate the data likelihood. So you have to evaluate the data likelihood exponential to minus phi of u for many different values of u. So you might have to evaluate it for tenth of thousands or even millions of different values of the parameters u. And if you then have a model where that is very expensive to do, that becomes computationally infeasible. Right? So if you think for the example that I gave you, where the evaluation of G, so the observation operator, involves the solution of a PDE, then every evaluation, so if you want to evaluate this data likelihood for a given value of u, that involves the solution of a PDE. And so this is very, very expensive. Right? And then if you have to do that tenth of thousands of times, that's just something that's not really computationally feasible. So what we do is we approximate either directly the log likelihood. So the phi here is what appears in the data likelihood. It just has this form that we saw here. Right? So the phi is just shorthand for this log likelihood term. So we either approximate phi or just the observation operator G, essentially the PDE solution, by a surrogate model. You might know that as an emulator or a reduced order model. It's just a model that is simpler than the original model, so it's simpler than the PDE. It's something that's faster to evaluate, but it still captures the main idea of the model, so the kind of the main behavior of the model. So there's very many different choices that you can use. So reduced order models is a very wide topic with a lot of active research there. So there's really a lot of things that you can do. So I've given you some references here, in particular in the context of inverse problems. What we'll be using is Gaussian process regression. So that's what we'll be using as our surrogate model or reduced order model. So that goes back long way in the spatial statistics literature. There's a couple of reasons why we like Gaussian process regression. One is that is what's known as a black box methodology. So all you have to be able to do to construct this surrogate model is you have to be able to evaluate your observation operator, right? So you just have to be able to evaluate G at n different points u. Right? So in the context of PDEs, all you have to be able to do is solve the PDE for a given value of the coefficient. And so whether this is a multi-scale PDE or multi-phase or multi-physics, it can be very complicated. That doesn't really matter for this method as long as you're able to solve it. That's fine. Having said that, you can try and make it kind of a gray box methodology where you are using some of the constraints that you have. For example, that you're solving a PDE, and I'll come back to that later on. Another thing that we like about Gaussian process regression is that it is a Bayesian procedure, which gives you uncertainty quantification. And I'll talk a lot more about that later on, because that's really the main part that Gaussian process regression, because it is Bayesian, it doesn't just give you one reduced order model, but it gives you a whole probability distribution on reduced order models. And that's something that you can use in the inverse problem. But as I said, I'll emphasize that a lot more later on as well. Right. So how does Gaussian process regression work? Right, so we now want to use Gaussian process regression to build an emulator or a surrogate model or a reduced order model, either for the log likelihood phi or for the observation operator in our inverse problem. For simplicity, here I'm restricting to the case where you have a scalar valued function. And so you could, for example, be emulating one of the entries of your observation operator. The way Gaussian process regression works, again, it's a Bayesian procedure. So you choose a prior on your unknown function f, and then you update it with data. As the prior, you choose a Gaussian distribution. So this is now a Gaussian process distribution. So it's a Gaussian distribution on functions. The way it works is that you have your unknown function f. If this is a Gaussian process, that means at every point ui, you now have a Gaussian random variable. So if you look at, for example, the point -1 here, then at this point, your process f would be a Gaussian random variable, which in this case has mean 0 and then standard deviation 1. So the mean of f at the point is given by 0 in this case. So you'd have a mean function. And then the covariance between points is given by this covariance kernel k. Yeah. But essentially, at every point ui, you now have a Gaussian random variable. And so if you look at sample paths of this distribution on f, you get functions that stay close to the mean, right? So they all stay close to 0, and then they fluctuate around the mean with a size that's proportional to the standard deviation that you've chosen. So this is the prior, and as I said, you do the standard prior to posterior update by conditioning on data. What is the data that we have here? Well, we generate the data using point values, right? So we choose capital N points UN in the domain of f, and then we evaluate f at those points, and then we just condition the process on going through those points, right? So that we here, that would correspond to observing these black dots. We've observed a function f at those points, and then we're conditioning the Gaussian process on going through those points. Okay. The nice property of Gaussian processes, because everything is Gaussian and linear here, you still get a Gaussian process. So even this conditioned Gaussian process, f conditioned on d, is still Gaussian with an updated mean and an updated covariance. I've given you the explicit formulas here, but they're not really that important. You can write them down explicitly and you know what they are, but for the remainder of this talk, it's not important exactly what they are. Yeah. So then you get this updated mean and updated covariance function, and then you also get the updated sample paths, right? Because you've updated the distribution, and you can see that all of the sample paths go through the points that you have observed, because you're forcing it to go through those points by condition. Right? And so this Gaussian process posterior that we have, the Fn, it always goes through the observed points because we're conditioning on it, but then in between you have kind of this probability distribution on what your function f is doing in between the points where you haven't observed what it is. Okay. And so the mean, so the posterior mean that you have this MNF function, you can view that as a surrogate model for f. And then if you look at the process itself, the Gaussian process posterior Fn, you can view that as a random surrogate model for f. And as I say, it's reflecting the uncertainty that you have in f away from the design points Dn. Right? So we go back here, right? So if I've observed f at these points here at the dots, so I could either just use this black line and say, I think that's what my function f is, and then use that as an emulator. Or you can actually use the full process itself, and then you get this random emulator, which goes through the points that you have observed, but then in between does something random. And so you have those two options, which either give you kind of a standard deterministic surrogate model or a random surrogate model. Yeah. It is a surrogate model in the sense that it is a much simpler model that is cheaper to evaluate. Right? So if you, for example, think of the mean that we had, you can write it in this form. So that just follows from the formulas that I had on the previous slide. And so if you now want to evaluate this predictive mean at the point of u, instead of having to solve a PDE, you just have to evaluate this expression here, which is just a linear combination of your covariance kernel k and then some constants alpha. The constants alpha do take some time to compute, so that would have cost n cubed. But the thing is, you have to only do it once, and the n is typically small, right? So in our applications, or in the applications that we're interested in, the n is typically quite small, and that's because the n is the number of times that you have to solve your PDE. Right, so to construct this surrogate model, what you're doing is you're evaluating your original function f, in our case, the PDE model, at capital N inputs, And so the capital N is the number of times that you have to solve your PDE to construct this model. And so in practice, that would be quite small because you can't afford to do that very many times. Yeah. And just to give you an idea of the kinds of computational savings that you're getting from this, if you're looking at an example that's in 1 spatial dimension, 2 parameter dimensions, and we have observed it at n equals 20 points. 1 solve of the PDE implemented in Firedrake in Python on a standard laptop would take you about 0.3 seconds. And then just evaluating this predictive mean instead, so using the surrogate model instead, you get it down to about 10 to the minus 4 seconds. Right? So these are really substantial savings that you get in computational cost. Okay. So now coming back to the inverse problem, so kind of putting it all together, right? So we had our posterior distribution, right? So this was the distribution that we're interested in. This is the distribution of our unknown parameter u, given the observed data y. So this is really the object of interest. This is what we want to do computations with. So we might want to sample from it using Markov chain Monte Carlo, for example. But the issue is that evaluating this G is just very, very expensive. And so we can't really afford to do that in practice. Right? So what we do is we approximate G with the surrogate model. So we approximate it by a simpler model that's easier to compute with. For the rest of the talk, I'm assuming that we approximate G rather than approximating the log likelihood phi directly. So rather than approximating directly this norm that we have here, but you can do the same and similar results hold for approximating the log likelihood. So you then have essentially, well, you definitely have these 2 options. You also have some more options, but you have these 2 options for using the surrogate model, right? So as I said, we want to approximate G. Because the surrogate model that we've constructed is stochastic, right? So our surrogate model Gn is a Gaussian process, right? So it's a stochastic model. You can also think of it as having a probability distribution on surrogate models. So you don't just have 1 surrogate model, but you get a probability distribution on the space of surrogate models. That is your stochastic Gn. And so you can think of doing 2 things. So one is you can think of just using the expected value of your surrogate model here. So instead of using G, you're now using MNG, right? So you're just using the mean of your stochastic surrogate model. If you think in terms of the probability measures on Gn, you're really just, because everything is Gaussian, the mean is the mode. And so you're using the most likely surrogate model here. Or you can think of doing something like this marginal approximation, where you're not just plugging in the mean, you're plugging in your full random surrogate model Gn. And then you're taking the expected value at the level of the likelihood. Right? So this is the marginal approximation where you're plugging in the full random surrogate model Gn and then marginalizing out the distribution. So the expected value here is an expected value over the probability distribution of Gn. So both of those things make sense, and both of them have advantages and disadvantages. So advantages of the mean-based approximation is that it is simpler, right? You're just using the mean here, and you don't have to compute this extra expected value. But then in this mean-based approximation, you are throwing away a lot of the information that you have, right? You're only using the mean of your stochastic surrogate model. And so you're throwing away any form of uncertainty quantification or probability distribution that you have, right? If you have a lot of data, then it doesn't really matter which of the 2 you use. So both this mean-based approximation and the marginal approximation converge to the true posterior as n tends to infinity. Right? So if you have a lot of data, you wouldn't really see a big difference, and both of them are very good approximations to the true posterior. If you're interested in this analysis, we have done a lot of analysis here. I'll refer you to these papers, and essentially you just need convergence of your surrogate model. So you just need to know that the surrogate model that you're plugging in to the Bayesian posterior distribution converges to your true observation operator G in some sense. Okay. So for large n, and as n tends to infinity, there's not going to be much of a difference, but it turns out that if you only have a small number of data points, then there is a significant difference. And remember, this is the case that we're typically going to be in. So if you're only able to solve your PDE a small number of times in order to construct the surrogate model, then this is the situation that you'll be in. So the way that the mean-based approximation and the marginal approximation look like can qualitatively be very different. I've given you an example here. So this is again a PDE example, which is in one spatial dimension, and we're inferring two parameters in the diffusion coefficient, and we have conditioned on 20 points. We have 20 training points for our surrogate model. Here I'm showing you different posterior approximations. So these are the posterior densities pi yn mean and pi yn marg. They are for the two parameters. So this top plot here is the marginal posterior for the first parameter, and then this bottom plot is the marginal posterior for the second parameter. And then we have the joint posterior of the two parameters here in this last plot. Yeah. So we have three different posteriors here. So the blue line is the mean-based posterior. So it's the pi yn mean. That is the blue line. The orange and the green line are two different versions of the marginal posterior. And you can see that they, one, look very different. And two, what I would argue is that the marginal posteriors are actually looking better than the mean-based posteriors. Okay. So why is that? So the dotted line, or the dashed line that we have here, so the vertical dashed line, is the true value of the parameters. So for the first parameter, we know that it's here, and for the second parameter, we know that it is here. And for the mean-based approximation, so the blue line, you can see that it essentially leads to biased predictions with high confidence. What does that mean? Biased prediction means that it's concentrating at the wrong spot, right? So you can see in this graph here, for example, that the peak of the posterior is quite far away from the true value. And at the true value, you're actually not giving a lot of density, right? So that density is already very small at the true value. And so what it's saying is essentially that you don't think, or you're not giving a lot of probability to the true value of the parameters. And it's even worse for this one here, where the mean-based approximation is already essentially zero at the true values of the parameters, right? So it's giving weight to the wrong part of the parameter space, but it is doing that with high confidence in the sense that it's quite a narrow distribution, right? So the prior on the parameters here is between -1 and 1. And so the prior was between -1 and 1. And you can see that the width of the posterior, so if you just look at the width of the blue curve, you can see that that is quite narrow compared to the full support between -1 and 1, right? So what this blue line is telling us is that I'm very sure that my true parameter is in this area, but it's really the wrong area, right? Because you're not actually including the true value. Okay. So compared to that, the two marginal approximations that I have here are doing a lot better in that sense. So in particular here, you can see the green one. The bias is a lot better, right? So we've actually shifted towards the true value. And two, it's also a broader distribution, so it doesn't have as high confidence as the other one. It's broader, and you can see that in this picture here as well, that it's kind of broader distribution, saying that I'm actually not very sure what the right value is. And you're substantially increasing the value of the PDF, so the probability that's given to the true value. Right. Why is that the case? Well, that's the case because in the marginal distribution, you are actually using the uncertainty that you have in your surrogate model. Right. So there you are using the full emulated GN. So you are using the full Gaussian process GN that you have and not just its mean. And that allows you to kind of model the error or the uncertainty that you have in your surrogate model. And that's how you're getting these better predictions and this kind of getting rid of these high confidence biased predictions. Yeah. So how do we actually compute these approximations? So it turns out that for Gaussian process emulators, you can compute this analytically. Right, so in general, you have this expression for the marginal likelihood where you're plugging in your random surrogate model here and then taking the expected value of the likelihood. When this random surrogate model GN is Gaussian, it turns out you can actually compute this expected value analytically. Right, so it just turns into an integral. Right, so if your GN is a Gaussian process, then at a point U, its mean is just the mean MNG at U, and then you're adding on the standard deviation. Right, so this is just the standard decomposition of a random variable into its mean plus the standard deviation part. We've just separated out the mean, and so the psi is then just mean 0, and then the same variance Kn. Right. And so what you can do is instead of the GN, you can plug in the MNG plus psi. So that's what we've done here. And then the psi is normal with mean 0 and variance Kn. And so then you can just integrate over the density of psi, right? So it's now an expected value over psi. Psi is just normal, so you get this density, and then you're just integrating over psi. And then you can just complete the square, and what you end up with is this expression here. Okay. So what you can see is for the marginal likelihood, you get this expression. So this is the one that I just showed you on the previous slide. What you end up with here is just the mean inside here, and then you essentially get an extra factor of the sigma of U, so which was just the variance of your Gaussian process emulator added on to the observational variance gamma. And so if you compare that to the mean-based likelihood, where we just had the mean as the surrogate model and then just weighted by the observational noise gamma, you can see that you get a form of variance inflation, right? So you're adding this sigma of U onto the variance that you have in the likelihood, and that's why you're seeing these broader posteriors, right? You're forcing the likelihood to have a larger variance, to be flatter, and that's why in the end the posterior distribution gets broader and flatter as well. So essentially, these marginal approximations are just variance inflation, and that's of course not something that's new. So that using variance inflation kind of as a tool to improve Bayesian inference has been used quite a few times over the last decade or so. Giving you some references here. It is of course also related to the inclusion of modeling error. So that's something that's kind of well established in the spatial statistics literature, dating back to this paper by Kennedy and O'Hagan from over 20 years ago. So in that situation, you would have a model like this. So you would assume that the observed data, again, comes from your observation rate, G of U, plus the observational noise. So this is the expression that we had earlier. And what you're now doing is adding another term, eta tilde, onto it, which is supposed to represent modeling error. So this is supposed to model the difference between the real world and your mathematical model, right? So in the PDE application, it would be the difference between the PDE that we have and the actual real world model, right? So there might, for example, be some missing physics, that there's some friction terms we need to take care of, or something like that, that we haven't included all of the necessary physics in our model, and that would come into this modeling error. Right? So it's also related to that. But what we're using it for is not to model the error between the real world and our model. We're using it to model the error between our model and the surrogate model. Right? So it is a slightly different interpretation, but a similar thing. Right? So using Gaussian process regression to do this variance inflation has a couple of advantages. So one thing is that you get a parameter-dependent inflation, right? So in this, in the literature on modeling error, the eta here is usually, or the eta tilde, is assumed to be independent of your parameter u. Most of this is done as a simplifying assumption, just because you can't really deal with the situation where it does depend on u. So for simplicity, you assume that it's independent of you. But again, I mean, the difference between your surrogate model and the true model, that would depend on you typically. And so having this dependence having this dependence on you kind of makes sense more intuitively, assuming that the error in your surrogate model is also dependent on you. The variance sigma of u is easily computed, so it's something that you get for free when doing Gaussian process regression. So typically when you include this modeling error, one of the big questions is, how do we estimate it? Usually people assume it's normal, and then you have to estimate the mean and the covariance, but how you do that and how you end up with having things that are identifiable, it's not very easy to do. And so having something which you can just get for free and don't really have to estimate or assume any specific structure on is something that's very nice. And furthermore, it's readily tuned because it is just the variance of a Gaussian process in Gaussian process regression. And so that's something that has been used for a very long time. And so there's a lot of literature on how to kind of tune this to get good results. Okay. Right, so in practice, you then have to think about how to actually sample from these approximations. So we now have our mean-based approximation and we have our marginal approximation. We've seen that the marginal approximation corresponds to a variance inflation, essentially. In practice, you then still have the question of how to actually sample from these densities. Typically, you would use something like Markov chain Monte Carlo, so this Metropolis Hastings algorithm, which I think many of you will have seen before. So this is just an algorithm for producing samples from a target density, which is called pi, which in our case would either be the mean-based posterior approximation or the marginal posterior approximation. It's a sequential algorithm, so you choose a sample U1, and then given U1, you produce U2, given U2, you produce U3, and so on. So given a sample UI, you produce the next sample UI plus 1 by proposing this new state U prime and then accepting it with a certain probability alpha here. So that's kind of the method of choice for producing these samples. In practice, it's really important how to choose these proposals. So this proposal density Q that you have here to generate your U prime, you have to be able to choose that well. In particular, if you're in very high dimensions, which is typically the case in these PDE-based inverse problems, that you have very high dimensional parameters U. And so you want to be able to do something like MALA, so the Metropolis adjusted Langevin algorithm, where samples look like this. So you take your current state UI, and then you kind of perturb it. So you move in the direction of the gradient of log pi. So this is designed to make you step in the direction of high density, right? So you want more samples in regions where the density pi is high. And so you want to kind of step into those regions, and then you have kind of a random step size, or kind of a random walk perturbation here. So that's typically kind of one of the methods of choice. Typically in PDE-based applications, this gradient is very complicated to compute, right? So if you need the gradient of pi, that would involve the gradient of your PDE. And so that's typically difficult or impossible to compute. But with these surrogate models, that becomes a lot easier, right? You don't have the PDE, you just have these linear combinations of the kernel functions. And so that's something that you can compute explicitly. Right, so that becomes quite easy. And then if you have a prior that's not smooth, computing this gradient can also be a bit complicated. But again, there's a lot of literature on how to deal with non-smooth priors, for example, using these Moreau-Yoshida envelopes. Okay. So then we have these methods, right? So we have good MCMC methods for actually sampling from these posterior distributions. So in the last part, I wanted to talk a little bit about specifically enhancing this methodology for PDE-based problems. So far, nothing I've said has been specific to the PDE problem, even though that's the example that I keep coming back to. Right? But everything really applies for completely general inverse problems and completely general observation operators G. Because our observation operator G is vector valued, right? So typically you would have more than one observation. So the Y is more than one dimensional. So this is a vector valued function. And so when you choose a prior on G, what you have to do is you have to choose a matrix valued covariance kernel, right? So if you're emulating vector valued functions, the K at UI and UJ, that is going to give you the covariance between G of UI and G of UJ. And if G is vector valued, that will be a covariance matrix, right? So you have to then get the required covariance matrix. The simplest thing that you can do is to just emulate all of them independently. So you just take the dy components of G, and then you just emulate each component independently. That corresponds to choosing this covariance kernel K as a multiple of the identity matrix, right? So then you're not putting any covariance in between the different components of G, because that's all zero, and you just have one covariance kernel K tilde. Right? So that's what we've done in this orange line that I showed you earlier. So this is exactly the same figure that I showed you earlier, where the blue line was the mean-based approximation, and the orange and the green line were two marginal approximations. For the orange line in the marginal approximation, we have just emulated all of the entries independently. So we haven't used that the entries of G are correlated. In the green line, we have. So the way that we get the green line, and you can see that that's doing even better in getting to the true value of the parameters, is that we have used that we expect the entries of G to be correlated. Right? So if you think of the PDE application, the data that we have is just the PDE solution P at different points xi. Right? And so if you're looking at different components of G, this would correspond to P at xi and say P at xj. So because it is the same function P evaluated at 2 points, and it is a continuous function, you would expect those to be correlated, right? And particularly if the xi and the xj are very close together, then you would expect the P of xi and P of xj to also be very highly correlated. Right. So how do we do that? So to get this spatial correlation included and to define correlation between the different entries of G, we go back to the PDE level. So we first define a Gaussian process on the entire PDE solution P. So we're now looking at P as a function of X and U. And then we're putting a Gaussian process prior on it with mean 0 and a separable covariance kernel. So we just have a K1 at U and U prime, and then K2 at X and X prime. Right. If we then want the corresponding prior in observation space, so if we now want the prior on the corresponding G of U, which is just P evaluated at the finite number of points xi, then we essentially just use that a linear operator applied to a Gaussian process is again a Gaussian process, and you know what the mean and the covariance are just in terms of the linear operator that you're applying, right? So in this case, the linear operator is just point evaluations. So we're just looking at this GP evaluated at points xi, which gives us that it's mean 0 with the covariance function given like this. So we just get K1 at U and U prime, and then we get this matrix K2, which is just your covariance kernel K2 that you chose in X, and then evaluate it at the observation points xi and xj. Right? So we're getting the correlation from the PDE by first putting a PDE in the continuous space, so on the PDE solution, and then pushing that forward into our observation operator G. And as I said, this essentially just uses that G is linear, and so you can extend that to any linear observation operator. The question is then what you choose for your kernel K2. You can just use something standard like a Matern kernel or a Gaussian kernel, and that's what we've done in the green line, and you can see that that really already does give you a substantial benefit. You can instead also use kernels from physics-informed machine learning, or physics-informed Gaussian process regression, right? So the K2 is really the covariance kernel that you have in the spatial variable X. And so if you want to include something like, I know that I'm solving a PDE, that's really the part where you have to include it, right? So there's a lot of things that you can do, and I would refer you to this recent survey here on kind of all of the constraints that you can put onto GP regression. Let me show you a little bit what you can do. So including boundary conditions is something that you know how to do. You can, to some extent, model monotonicity. If you, for example, know that you have a monotonic function, you can incorporate that your PDE solution or parts of the PDE solution are divergence-free. That's something that you quite often see in applications. In 1D, adding boundary conditions is very easy because you can just use them as extra training points, and that can really have a very large effect on the accuracy that you have. You can also incorporate really that you're solving a PDE, right? So if you think of the example that we had in the beginning, where we're solving this PDE, so we have a linear operator L that is this diffusion problem, and we know that's equal to G. What you can do in this case is actually incorporate the PDE operator L of U into the Gaussian process regression as well. So in that case, the way it works is that you put a joint Gaussian process prior, not just on the PDE solution P, but also on your right-hand side G. You first put a prior on P, like we did before, and then you get a corresponding prior on G, again by pushing forward the Gaussian process through the linear operator L of U, right? So it's crucial that L of U is linear, and once you've put a prior on P, so once you have this prior that you have here on P, you can apply the linear operator L of U to it to get a corresponding prior on G, and then you just, in addition to conditioning on point observations of P, you then also condition on point observations of G, which are usually very easy to obtain. And so that then allows you to incorporate the PDE constraint as well, right? If you're interested in this approach, that was really pioneered in this paper here, and there's more details on it there, right? So let me just quickly show this last figure. So this is now a figure which compares two or three different marginal approximations. So in this figure, all of the posteriors or all of the approximate posteriors are now marginal approximations. The blue one is one without any correlation. So we're modeling the G as independent processes. We're not including any correlation between the different entries of G. The orange one is the one where we include spatial correlation, but it's done with a standard Matern kernel. And the green one is the one where we use this PDE-informed kernel, right? And you can see that you're kind of always getting a bit better. So adding the spatial correlation seems to have the biggest effect. So going from the blue to the orange line, and then the green line, so including that it is a PDE, does give you a bit of a benefit as well. If you have more complicated models or more complicated PDEs, we do see a bigger difference. So in this case, because it's just a diffusion problem in 1D, you don't see that much benefit from including the PDE constraints as well. But you do see a little bit. All right, so that was really all I wanted to say. So we discussed how you can use surrogate models to obtain computationally cheap approximations to Bayesian posterior distributions that you can then use for simulations in practice. We particularly looked at Gaussian process regression, which is a very popular choice of surrogate model. And in particular, we focused on how we can use the predictive variance. So this Kn, the variance in the Gaussian process regression, how that can be used to define this new marginal approximation, which is usually better for Bayesian inference, rather than just using the mean-based approximation where you ignore the error in the circuit model. Right. So we have a paper on this in preparation. We're hoping to have it submitted by the end of this year or early next year. For now, I can point you to some of the references. So there's this paper here, which I said has a lot of the theory and kind of sets up the different approximations to the posterior. So it's kind of the foundations and theoretical side of this work. Okay, so that was all I wanted to say. So yeah, thank you very much for listening, and I'm happy to take any questions if